Hello, Professor.
Hi. Hello, guys. Good to see you. Okay, as I mentioned last time, we still have quite a big piece of material to be covered during this discussion. So I think let us try to be productive and start doing that. So definitely something will still remain for your consideration with the textbook, but I hope we will cover in our discussion most relevant concepts, so we have a chance to be familiar with them before you read the chapter, or maybe for someone who already did that, it will be just a chance to polish it a bit, this understanding of the concept of torque and angular momentum. So let us start. We'll try to change the camera. Oh, good, it even works now. So, as I mentioned, we will start from discussing the concept of torque. And this is because we continue looking for analogies between translational and rotational moments. So we considered analogies in kinematics of these two types of motion and also in kinetic energy. So we had a chance to describe the concept of, introduce the concept of a moment of inertia and learn how to calculate it for different cases. Now we need to compare the translational and rotational motion in terms of forces which are exerted on bodies. So if there is some force exerted on a rigid body, which can, like, fixed in that way that it can rotate about some axis, fixed axis, this force will, the body will most likely start to rotate if we don't have any friction, so it starts to rotate about this axis. And the tendency of the force to rotate this body will be described quantitatively by the torque. And it has this denoted as tau, and it's actually a vector quantity, but we will come to this discussion of vector nature of torque a bit later. Now we need to define its value. And in order to do that, let us consider some system, a bolt with a wrench. Have some wrench. Looks like a fork, but never mind. Okay, so we have some axis of rotation, which is axis O, goes through the center of this ball, perpendicular to the image plane. And let us assume that somewhere here we exert a force F vector. So have X, Y direction, and here will be Y direction. So this force is applied with the angle to the axis X. Let's call it angle phi. And now we have two components of this force. One will be like X component will be F times cosine phi, and here will be Y component will be F times sine phi. So the torque, the tendency of rotating this system, rigid system of bodies about axis O, will be defined as the following. So its absolute value will be R times force times sinus phi. And R is actually our position vector with respect to this point where we apply the force F with respect our axis of rotation O. And this is equal to F D. So let us define what is D. If we draw a line which goes through this vector F, it will be a line of action of force F. And the perpendicular which goes from the axis of rotation to this line of action of force F, this is right angle here, it's our D. So D is equal to R times sinus phi, because if we have this angle phi here, here we will also have this angle phi. And from the right angle triangular, we can define D as this, as R times sinus phi. And what is important, it's an important parameter. This D is called moment of a moment arm or a lever arm of force F with respect to axis O of rotation. So if we consider, for instance, this X component of force F here, which goes along axis X and goes directly through the axis of rotation O. In this case, its torque will be equal to 0. It will not have any tendency to rotate the system because it's on the same, acting on the same line which goes through the axis of rotation, and then the moment arm will be equal to 0. So that's another, so that's really important orientation of the applied force with respect to the axis of rotation. That will define the that will define the tendency to rotate the system. So the units for torque now is Newton times meter. And please don't mess it up with units of mechanical work. It's also Newton meter. So here is the different concept. It's about rotation, and keep this in mind, but units are the same, Newton times meter. So once we define this, or also I think it will be reasonable to mention before we proceed further, if we have some rigid body and let's say this is our axis of rotation, O, and there are two forces, F1 and F2. So now let us show the lines of action of these forces. And we know that these perpendiculars from the axis of rotation to lines of action of forces will give us the moment arm. So it will be D1, it will be D2. But we see that because of orientation of these two forces with respect to the axis of rotation, they tend to rotate the rigid body in different directions. That's why the net torque will be the sum of torques originated from two forces, which will be F1 D1 minus F2 D2, since they tend to rotate in different directions. If they would tend to rotate in the same direction, we would just sum up torques originated from each forces exerted on a rigid body. With respect given axis of rotation, that is very important. You always need to specify and keep this in mind. Okay, so let us consider a rigid body with constant, with some like net torque applied to it. Go further and consider such system. We have X and Y, some rigid body. This is our axis of rotation, which is at the origin of system of coordinates, O, so it goes perpendicular. The axis of rotation is perpendicular to the plane of our figure. Then we select one like very tiny mass of this rigid body, dm, which is defined by position vector r. And there is, so since it rotates, this small piece of rigid body will go like follow some circular trajectory. And there is some tangential net force which is applied to this little piece of the rigid body. It's tangential, so it's always perpendicular to the radius position vector r, and we denote it as df, tangential. So we know that by definition, according to the second law of motion, we can write that df tangential is equal to dm times a tangential. So it's linear tangential acceleration. And now we need to calculate the external torque, which is associated with this force dFt. So d tau, it will be equal. So we know that it's equal to the product of the absolute values of two vectors. So we are talking about here about absolute values. Vector nature of torque we will discuss a bit later. So it's product of two vectors, distance from the origin, from the axis of rotation, force, and then sinus of angle between these two vectors. So since tangential force is perpendicular to the radius vector, the position vector, we can write that it's just a product of r times dft. And assuming the definition of this force, we can write that it's r times dm times at. Okay, so now we can recall what is the relationship between linear velocity and angular velocity. As you remember from our previous discussion, linear velocity is equal to r times omega, where omega is angular frequency, like angular velocity. So from here, if we take a derivative, we will get dv over dt is equal to at, tangential acceleration, and this is equal to r, since it's constant for this circular motion, which we consider now, times d omega dt. And this d omega dt is nothing else as angular acceleration, which we denote as alpha. And this is convenient to go from tangential acceleration here to linear acceleration, to angular acceleration, because angular acceleration is, as you know, the unique parameter which describes all parts of the body. So it's the same for all parts of the body, as opposite to linear acceleration and linear velocity. Okay, so let us now substitute this linear tangential acceleration by its expression via angular acceleration. So we can write that d tau equal to r dm times r alpha. And yeah, so we actually get r squared dm times alpha. And assuming that alpha is constant for all parts of the body, the net, like total torque, which is applied to the rigid body, let's call it external, will be equal to the integral of alpha r squared dm. So again, this alpha is constant for each dm, for each part of the rigid body. So we can put it in front of the integral of r squared dm. So does it recall something in your memory from our previous discussion? This is, this is I, the moment of inertia. This definition of how we calculate moment of inertia. And that means that the total resultant torque on a rigid body is equal to the product of moment of inertia to angular acceleration of this rigid body, which is again moment of inertia. We always keep it in mind that this is calculated with respect of a given fixed axis of rotation. So this is kind of second law of motion written for rotation of rigid body, because we know that resultant force is equal to mass times acceleration, linear acceleration. And here we can write that resultant torque is equal to moment of inertia times angular acceleration. So again, we have this analog between translational and rotational motions, but use just different terms to have the same forms of these equations. Okay, so we define what is the torque and how it's defined for rigid body, which are under rotation. Now let us go further and try to figure out the angular momentum, the concept of angular momentum, and how we can calculate. Okay, so in order to introduce this concept of angular momentum, we need first to define the vector nature of torque. So I mentioned previously that we will discuss this moment, and let us do that. So in order to do that, we need to recall cross product of two vectors and its features, because in order to define the direction of torque vector, we need to operate with this vector product, the cross product of vectors. So let us recall first properties of vector product. Let's say we have two vectors, A and B, and there's some angle P between these two vectors. What will be the cross product of two vectors? Usually it's written like this. So it will be some vector C. You see already the difference between dot product of two vectors when we get a scalar number, and cross product of two vectors, so we end up with a vector. And this vector, its absolute value will be equal to A times B times sinus phi. So it will be area actually of this parallelogram formed by vectors A and B, like this area. And its direction will be perpendicular to the plane defined by vectors A and B, always perpendicular, and the orientation, let's say up or down with respect to this plane, depends actually, is defined by the right hand rule. So if we point 4 fingers in the direction of vector A, then wrap them in the direction of moving vector A to B, first vector in the product to the second vector, in the direction of reducing angle phi between them. Then the right up sum of the right hand will show us direction of the vector C, which is in this case that goes perpendicular to this plane. It will be vector C equal to A times B cross product, and that's why if we have B times A, we just replace them in the product in order. We will get some vector, the same vector, but in the opposite direction. It will be minus C. So this is the feature of cross product. If we change the order of vectors we multiply, the resultant vector will be the same in magnitude, but it will be in the opposite direction. So these basic features we need to know. Also, it comes actually from here. If we have two perpendicular vectors and we get some cross product of perpendicular vectors, then the magnitude of vector C will be just product of AB. And if vectors are parallel, C is equal to 0. So the product of two parallel vectors will give us 0. And also kind of relevant feature of cross product, which should be highlighted, it is the derivative of cross product, d A B over dt, for instance, will be it will be following the rule of derivative of the product of two functions. So it will be dA dt times b plus a db dt. Okay. Yeah, pretty much everything what is relevant. Of course, you can double check in the textbook for more detailed information about cross product of two vectors, since it's an important concept which is used in physics quite often. So this part we are done, and now we can go for yeah, maybe, well, not done, so it just introduction of the cross product. So we need to define the orientation of our torque. So let us, based on this knowledge about features of cross product, let us have a three-dimensional system of coordinates, say x, y, and z. So we have some particle, and some force is exerted on this particle in the plane x and y. So this position of this particle in this plane x and y is defined by position vector r. So this is our origin of coordinate, and in this plane x and y. We are interested to calculate the torque and define its direction with respect to rotation about axis z of this particle when force F is exerted on it. So there will be, if we extend this position vector, there will be some angle P between position vector direction and direction of force F. So based on the definition of torque, it is now in vector form, is equal to the cross product of our position vector and exerted force. So taking into account the orientation of vector r and f, we can see, based on the right-hand rule, that our torque vector will be directed along axis z. So this is cross product of, actually it's not d, just of position vector and force. And it's perpendicular to the axis x and y and directed along vector z along the direction of axis z, and z is our axis of rotation, about which rotation of this particle is considered. So this is how we define the direction of the torque. And now we finally can start considering the concept of angular moment, once we already know how our torque vector is oriented. Okay, for this purpose, in order to introduce angular moment, we also consider a system of three axes, x, y, and z. We consider in the plane of x and y some particle with mass m, and let's consider that it possesses some linear momentum p. Remember how we define linear momentum? What is the equation for linear momentum? Who remembers? So linear momentum is the product of linear velocity and mass. And we also remember from the differential form of second law of motion that the resultant force which acts on the body can be defined as first derivative of momentum over time. Actually makes sense because it's m times dv over dt, and this is m times acceleration. So it's second law of motion, but just in differential form, which defined in terms of linear momentum. So let us write equation for the torque which exerted on this body with a mass m. So some resultant torque vector will be equal to the vector product, as we defined before, of our position vector and some resultant force which is exerted on this particle. So it is equal to r times the derivative of linear momentum. First derivative of linear momentum over t. Okay, so now what we can do? Let us add to this equation to the right side vector product dr d over dt. Yeah, it's vector product times p. So we can do this. We can add just to the right side. Why? Because this vector product is equal to 0. Do you see why this vector product is equal to 0? And there is no way or other option. So vector of linear momentum p, as I mentioned before, it's the product of mass and linear velocity. So means that vector of linear momentum is always parallel to vector of linear velocity. And dr over dt is nothing else as linear velocity. The product, that's why this is linear velocity first, and this is linear momentum second. So the cross product of two parallel vectors is equal to 0. So that's why we can add it to the right side of this equation, and we will get the following. The resultant torque will be equal to r times dp dt plus this part dr dt times p. And this is nothing else as the derivative over time of the vector product between radius vector and linear momentum. So we have vector product of position vector times linear momentum d over dt. Okay, since we have such a term as vector product of radius vector and linear momentum, we can introduce a new parameter, and this parameter actually is the angular momentum. So we can write that this is equal to dl vector divided by dt. So in this case, L is our angular momentum, is equal to the vector product of radius vector or position vector times the the vector product of position vector and linear momentum. So the units for angular momentum will be the following. So what we have linear momentum, and linear momentum is product of mass and acceleration. Then we have also another vector, which is position vector, which is just meters. So think about this a bit later, and you can write by yourself the units for linear momentum. So other from that, we introduce the concept of linear momentum and define how we calculate it. Okay, so now we need to consider the, so this is just some particle with mass m, but which is rotating about axis z. But we want to have some more general definition of angular momentum, which is applicable to rigid bodies, because we consider rotation of rigid bodies. So for that, let us consider a rotating disk about axis z. So this will be our disk. And on this disk, we pick up some small volume with mass mi, and it moves on this, like performs some circular motion around about axis z, and it possesses some linear velocity v, which is perpendicular always to the position vector r. So we can write based on previously derived equation for angular momentum. Our angular momentum equal to the radius vector cross product with linear momentum. So this is what we defined previously. Now we need to apply this in our case. So we will consider only absolute values. So for this particular case, it will be equal to the product of mass mi then velocity vector vi of this small volume of the disk, because so that is this product uses the linear momentum, and we also have Ri, which is the position vector. So we don't have any sinus, some angle theta, because angle between, as I mentioned before, angle between the radius vector, position vector of this small volume with mass mi, and the velocity, linear velocity is always 90 degrees, so sinus 90 degrees is unity, so we don't write it here. This will be equal, yeah, in this case, we want to go again from linear velocity to angular velocity. And we know that linear velocity is the product of radius to angular velocity. So let us substitute linear velocity in these terms. And we will get mi ri, ri, omega. Omega is the same for any parts of this disk. This is equal to mi ri square omega. And the total angular momentum of this rotating disk about axis z will be equal to the sum of these angular momentums of small volumes of this disk with mass mi rotating about the same axis of z. And in this case, it is sum over all I, mi ri square omega. And since omega is a constant, we have omega times the sum over all I, mi ri squared. And this is nothing else as, again, our moment of inertia, I. So we can write that the total moment of angular momentum about axis z of this disk will be equal to the moment of inertia times omega, angular velocity. Again, it's analog of, so this angular momentum is analog of linear momentum for translational motion, because we have P times mv. We have a product of mass to linear velocity. But for rotational moment of rigid bodies about a fixed axis, we have a product of moment of inertia to angular velocity. If we take a derivative over time, so it will be dLz over dt equal to the sum of like some resultant torque. We know it from previous slides. We already derived this expression and the relationship. And what we learn now, it will be moment of inertia times d omega dt, and this is moment of inertia times angular acceleration alpha. So we derived before this expression when we defined the torque. Then we derived this equation when we defined angular momentum. And we see that they are related to each other in the bigger picture of rotational motion of rigid bodies. So there is a clear dependence between the angular momentum, change of angular momentum, and moment of inertia and angular velocity, and also change of angular momentum and some resultant torque, which applied to the body with respect to this axis of rotation. And it's also defined by the product between the moment of inertia and angular acceleration. So another important thing before we finish, we are running out of time, that in analog to linear momentum, angular momentum also follows the conservation law when we have isolated system. So isolated system for a rotating rigid body will be considered as a system when the net torque is equal to zero. So net external torque exerted to the system is equal to zero. So analog to the isolated system for in terms of linear momentum, when net force, external force, is equal to zero. Here is net torque, external torque, equal to zero. And if this is the case for such isolated system, we can see it from here. If external torque is equal to zero, then change of the moment of angular momentum for the rigid body rotating about given axis, in this case axis z, will be also equal to zero. From here, we can make a statement for the conservation of angular momentum, where Lz is equal to constant. So means that from the definition of angular momentum in terms of moment of inertia and angular velocity, initial moment of inertia times initial angular velocity will be equal to the product of final angular velocity, moment of inertia and angular velocity. So means if for the isolated rotating rigid body, if all external torque are compensated, if we change, for instance, decrease the final moment of inertia with respect to initial moment of inertia, that means that final angular velocity will increase with respect to the initial angular velocity in order to keep this product constant. That's why how you can calculate change in angular velocity when you increase or reduce moment of inertia. What is observed in real life in the skiing, when you neglect with friction and you start to spin, rotate and put your hands close to your body, you reduce the moment of inertia, and that causes, based on the law of conservation of angular momentum, increase in your angular velocity. So you do more revolutions per minute than before. That happens because of conservation of angular momentum. Okay, so we already run out of time. I wish you good evening, and I guess we discussed all major parts of the topic rotation of rigid bodies about fixed axis. So do you have next week a break, like fall break? Okay, good. So then we don't have lectures during the next week. Try to relax a bit. Maybe who feels that was too much material, maybe you have an option to read a bit more and try to understand. If you have any questions, then starting from next week, like in a week, on Monday, we will have lectures, and you're welcome to ask questions. Okay, guys, thank you very much for attention, and have a good break. Relax and get ready for the second part of the semester. Have a good evening. Bye.